Hello to all of you. In the previous lecture, we studied Chapter 2, Steady State Diffusion, and we discussed the introduction to this chapter, and then we studied the one-dimensional steady state diffusion, and we showed you how to generate the grid, a simple grid, and we discussed how the discretization process goes on, which included the explanation of what is the diffusion coefficient and what it represents, and also the gradient flux and what the meaning of the source term. Then we studied the solution of this discretization process by using the TDMA, which is the tridiagonal matrix algorithm. All of these topics we introduced, it was for the specific for the Cartesian coordinate, and we also solved 3 examples. Each one have different boundary conditions so as to practice how to deal with such boundary conditions. Today we will continue with the part 2 of this chapter, and we will study the 2-dimensional steady-state diffusion, and we will take an example and we will solve it. Then we will study the 3-dimensional case study for the steady-state diffusion, and in this way we will we will finish the Cartesian coordinate, and then we will give you an idea and the solution method for the polar coordinate system for the one-dimensional steady-state diffusion, and we will give you a homework after we discussed how to discretize such a problem. Then we will end this chapter with the spherical coordinate system with, of course, the one-dimensional steady-state diffusion, and we will take a few projects, unsolved project, as a practice for your homework. So let's begin this part of lecture. As we said, we will study the 2-dimensional case study of steady-state diffusion for Cartesian coordinate. As we see here in the figure 2.12, a domain of 2-dimensional domain of any engineering problem, and it is divided with a number of control volume in this direction called nx, and a number of control volume in the vertical direction, which is ny. So we will have a number of control volumes, and the governing equation will be as written as shown in the equation 251. Recall the general transport equation for the transport property phi in chapter 1. It included many terms. Since this chapter deals or study the steady state case, therefore the first term on the left of this general transport equation, which is partial phi by partial t, will be deleted because there is no change in phi with respect to time. And since there is only diffusion process, there is no convection, therefore there is no u vector equal to 0. Therefore the second term on the right, which is the convective term, will be also deleted, and therefore the only remaining thing will be the diffusion term and the source term. Since it is 2-dimensional case, therefore we will add to the 1-dimensional another part, which is d by d partial by partial phi gamma multiplied by partial phi by partial y, as shown in equation 251. The notation of this 2-dimensional grid, we will keep the same notation as the 1-dimensional case, which is P, capital P, which is the center of our control volume and focus, and big W, which is the center point of the control volume, which lies on the west side or the left side, and big E point, which lies on the center of the right or the east control volume. We will add to it another control volume with a center point marked as big N, which is at the center of the upper control volume of our control volume, and another point which is big S letter, which is at the center of this control volume, which lies on the south edge of our control volume. And we will add also another symbols, which is small n for the interface between the north control volume and our control volume P, and small s, which is the interface between the south control volume and the point control volume. The width of our control volume is this. It will be delta x, and the height of our control volume will be delta y. So to start our solution, we have to integrate our differential equation number 251 along the control volume. So since it is a two-dimensional case study, we will put here double integral symbol with a d volume of the control volume element, and also here double integral and d volume, and also here double integral and d volume. D volume, as we know, equals dx multiplied by dy multiplied by dz. Since the phi doesn't change with the z direction, therefore we will take a unit value for dz, and it will equals to 1. Therefore d volume will be equal to dx multiplied by only dy. And this sign of the double integral, this is from west to east and from small south to small north, and also from west to east and from south to north, and the same goes here and there. Sorry, we will delete this. Then we have to complete our solution by taking the second step, which is let us focus about this thing. We have here partial by partial x. This will be cancelled with this thing, a symbol, and this partial y will be cancelled with this dy. The only thing will be left here is this quantity, which takes this one, and here the second term will be left with this quantity, which will take since it is y, it will take this thing. So therefore, if we recall in mathematics simple integration process, if we have integral dy, it will give us y, because this integral sign will cancel the action of this d operator. Therefore both will be cancelled, and the only thing will be left y. If it is integral from 1 to 2 dy, therefore this symbol will cancel the activity of this operator, and we will find that y and substitute the limit of integration from 1 to 2, and this will equal 2 minus 1, it will be equal to 1. Okay, if these symbols are from west to east, therefore he will put west to east, and it will be y at east minus y at west. So if we have another symbol, let's take another symbol. If we have integral partial a, it will give us, this will go with this, a. Integral anything here, it will give us anything. So therefore, this integral sign will disappear with this partial operator. The only thing will be left here, it will be gamma partial phi divided by partial x, and will take this limit of integration, it will be from west to east, and also this sign will disappear with this partial operator, and this will give us gamma partial phi divided by partial y, and the limit of integration will be from south to north. Okay, this s phi, we can take it outside of the integration and we'll give it an average bar symbol, and the dv will be with integration will be delta v. Knowing that the area at x interface equals the area at the y interface equals w. If we focus on in figure 2.12, we will find that area at east is this side with the depth dz would equal to 1 unit. Therefore, this area will be equal to this distance, which is delta y, multiplied by 1 unit, which is dz. Therefore, area at x will be equal to delta y, and it is equals to area at west interface, which equals also to delta y multiplied by 1 unit, which is the dz quantity. Area at north side is this thing, this area. It will be equal to this distance delta x multiplied by the depth, which is dz, which is 1 unit, and the area at south interface, it will be equal to the same as before. It will be equal to delta x multiplied by 1 unit depth of delta z. So therefore, when we open the details of equation 252, we will have equation 253. This is the opening of the first integral, double integral on the left, and this is for the north and south term, and this is for the source term. Now we will open these derivatives by using the central difference scheme, which is the best accuracy among other schemes, that is the forward or the backward schemes, because it is the second order of accuracy, and it will give us a solution with the lower limit of error. Therefore, after opening these derivatives with the central difference scheme, we will have equation 254. And now we can assume this quantity, the average value of source term multiplied by delta volume, with a linear a function of phi p, which will be the slope of the function, which is sp multiplied by phi p plus a constant term, which is su. Substitute this equation 252 into equation 254 and rearrange it, and taking all the group that is multiplied by phi p and put it on the left hand side, and the resting parameters will write it on the right hand side. We will have equation 256. Rewriting this equation in the general discretization form, it will give us equation 257, and we can by examining this equation, we will find that a west is that parameter, which is multiplied by 5 big west, and this is A east, and this is A south, and this is A north, and this A west is the same as this one, and this A east is the same as this one, and the same goes for the other two, which is A south and A north. Therefore, all of this will be equal to A point, which is A west and A east, and this is A south, and this is A north, and SP will remain as it is. Now we will take focus on if it was a three-dimensional case study, steady-state diffusion for the Cartesian coordinate, and therefore we will see the control volume will look like the figure 213, which is a small rectangular shape body. It may be cube or parallelogram shape, solid one, which have 6 faces, and we will which is have the same notation as the two-dimensional case study, and adding to it another control volume at the top, which will have big letter T at the center of it, and another control volume at the bottom, which have a central point with a big B and at the center of it, and 2 extra nodes at the interface of the surface. The point small t will take the interface between the top control volume and our control volume, and which is centered at big P, and the letter small b will be drawn at the center of the surface of interface, which lies between the lower control volume and our control volume. Equation 258 shows us the governing equation of the three-dimensional case study, which is the same as the two-dimensional case, but adding to it the third part, which is the change of phi with respect to z. Therefore, it will be written as partial to partial z, gamma multiplied by partial phi to partial z. Okay, the question here, if we go back to the problem of the two-dimensional case study. Recall the problem of the one-dimensional case study. If any problem we want to solve it, we will make a discretization process, and we will end with a general assembly table which have 3 zones, 1 for the internal and 2 for the boundary condition, and by applying the data given in the question we will solve it. So that means our general assembly table in the one-dimensional case study, we will have 3 zones. The question here is now, how many zones do we have for the two-dimensional case study? You can pause this video and to think about it. Now we will give you the answer for this question. Suppose that this is a two-dimensional domain with a different boundary condition, and we want to solve this problem by starting with the discretization process, and we will end with a general assembly table. The first zone we will study and analyze is the core or the internal points of this two-dimensional domain. Therefore, one zone it's for the core, and also there is 4 ribs that surrounding this core. Each rib has an internal node, so the north side with an internal nodes, and the south side with a second internal node, and the west side with internal nodes and the east side with internal node. Therefore, 4 internal nodes for the ribs. Okay, this internal. And the only thing left is the corner. So this is corner number 1, this is corner number 2, and this is corner number 3, and this is corner number 4. Therefore, 4 corners. So by summation of these zones, it will be 9 zones. Okay, so the answer of this question is we have to do 9 zone discretizations process to reach the assembly table, and then we will substitute our data in these 9 zones to make our algebraic equation, which is equal the number of variable, and we will solve it by matrix or by calculator. So now we will give you the same question for the 3-dimensional case study. The question is, how many zones do we have to discretize in order to make the assembly table for the 3-dimensional case study, which is of course steady state diffusion. To answer this question, we will give you a small time, and you can pause this video to think about it. Okay, now we will give you the answer of this question. Let's start by assuming that our computational 3-dimensional computational domain is the figure shown in 2.13. So this small cubic shape, solid shape, it has one core, which is the core inside this cubic. It is one core, and it have 6 faces. Each phase, it represents a 2-dimensional case study. So therefore there is internal node for the upper face, and internal node for the lower face, and internal for the west side, and for the east side, and for the south side, and for the north side. Since it is 6 faces, therefore there is 6 internal node for face. 6 internal node for the faces. So how many ribs do we have? We have 4 ribs at the top side, and 4 ribs at the bottom side, and 4 ribs out the corners. Therefore we have 12 ribs internal. Each rib have an internal nodes. This 2, this is 3, and this is 4, and the same goes for the rest of this. So therefore 12 internal nodes for all the ribs. And we have how many corners? 4 at the top and 4 at the bottom. Therefore 8 corners, and that's it. And when we make a summation, it will give us 1 plus 6. It will be equal to 7 plus 12. It will give us 19 plus 8. It will give us 27 zone to be discretized in order to reach our assembly table. So it doesn't matter if it is transient case study or if it is steady state. The things is the values of the parameter will be changed, but the grid will remain have 27 zones. So let us continue our discussion of this. When we make integration, since it is 3-dimensional case study, we will make triple integration here with a dv, and this dv will equal dx multiplied by dy multiplied by dz, and the same goes for the second term and for the third term and for the fourth term. So when we substitute this integral with the lower and upper limit of integration, the same procedure as we did in the two-dimensional case study, then we substitute these derivative term with the central difference scheme, and we substitute the source term with the same linear function of phi, and when we rearrange the equation 259 and put all the group that is multiplied by phi point on the left side and the rest of the phi's on the right side, we will end with an equation, and we will, if we put it in the general discretization form, it will give us equation 260, and by focusing and comparing this equation 260 and the one before, we will find that these parameters which are listed in this table will be given as shown here. So A West will be gamma, the A West multiplied by A West divided by delta X West point, and the rest goes as shown. And the A point, it will be the summation of the A neighbors minus SP. Let's take an example for the two-dimensional case study. As shown in the figure 214, a two-dimensional plate of thickness 1 cm, this is 1 cm, is subjected at its west boundary at a steady heat flux of 500 kilowatt per square meter, and at the south and east boundaries there is a perfect insulation. If the north boundary is maintained at a constant temperature which is 100 centigrade as shown in this figure 214, and the thermal conductivity is constant, which is equals to 1000 watt per meter Kelvin, it is required to solve this problem and to calculate the temperature distribution in this plate using the finite volume method with a uniform grid of dx to Sawi delta x equals delta y equals 0.1 meter. Knowing that the two-dimensional steady-state heat conduction equation is given as shown in this differential equation: partial to partial x k dt by dx plus partial to partial y k dt by partial t to partial y equals to 0. First, we will write down the given data separately, just for the sake of simplify the solution. So we will write delta x equal to delta y equals to 0.1 meter, and delta z equals to the depth of this plate, which is equal to 1 cm, which equals to 0.01 meter. K equal 1000 watt per meter, and the rest goes for the boundary condition. The flux at the west equals to 500 kilowatt per square meter, and there is no heat flux, which is equal to 0 at the east and south surfaces, and also temperature A equals 100 at the north, and area at east and west equals to area at x equals to delta y multiplied by 0.01 meter, and area north equal to area south equal to area at y section equal to delta x multiplied by the same depth 0.01 meter. Delta x west point equal delta x point east equal delta x, and the same goes for delta y. As we see here, we have to divide the domain into a number of control volumes in the x direction and the number of control volume in the north direction. Since the question is forcing us to take the value of delta x equal delta y equal 0.1 meter, and since we have the width of this plate which equals to 0.3, therefore nx will be equal to 0.3 divided by 0.1, 0.3, sorry, divided by. Therefore, we will have 3 control volume in the x direction, and ny will equal to the height, which is 0.4 divided of delta y, which equal to 0.1, and it will be equal for control volume in the y direction. Okay, let's delete these marks because we need a clear space to describe other things. Okay, as we see here, we have the vertical line which passes through the force control volume. About the numbering of the control volume, we can number as shown here: control volume number 1, 2, 3, 4 in this vertical direction. Then we continue to the second line, number 2, the same numbers 5, 6, 7, 8, and we continue the third line, which is the vertical, 9, 10, 11, 12. So we have 12 control volumes numbered as shown by these lines, according to these lines, which passes through the center of these control volume. Or we can number in the horizontal direction, which will be line 1, or this line 2, or this line 3, and this line 4. That means 1, 2, 3, 4, 5, 6, and the same goes to the last control volume. So we have 2 choices, and we have chosen the first choice with the vertical 3 lines. So now as we said before, we have to discretize this problems 9 times. Each time will cover a specific zone. We will start by the internal nodes, which are only nodes control volume number 7 and 6, which are away from the boundaries, and therefore we will have 9 zones. It will be as shown in this assembly table. Each zone have a different value of parameter. If we see here for the internal nodes, all the A west, A east, A south, A north have specific values, and there is no source or SU parameter values. But for node number 2 and 3, we have a 0 value for A west, and a quantity of SU equals to the flux multiplied by area at X. Therefore, this table will represent each value for each zone. So after this, we substitute the value that is given in the question into this table, and we will make a number of algebraic equation which equal the number of control volumes, and that is 12 algebraic equation which hold 12 variable which start from T1 until it goes to T12. These are the 12 algebraic equation after the substitution of the values, and we will make these 12 equation and rewrite it into a matrix system, and which will be given as the matrix system that is shown here. Since this is a matrix with a 12 by 12, it is therefore we can solve it by using MATLAB or by the scientific calculator, and directly, and to give us the solution of this temperature vector. We have 3 methods to solve it directly, either the Gauss elimination method, the direct one, or the iterative method, the Jacobi and Gauss-Seidel, or the relaxation method. But since this is not a tridiagonal method, because it have another lower matrix and the upper matrix, it will be cannot be solved by using the TDMA method. Another thing, this is even it is a small matrix, but maybe we have a research and we want to do a 2-dimensional or 3-dimensional case study, and the matrix will be more than 12, maybe 20 by 20 or 400 by 400. It depends on the resolution of the grid. Therefore, it will require a large computer memory, and this could be very expensive to a specific case study, and which will require us to buy an expensive computer. There is another alternative, that is dividing this matrix into a number of sub-matrices. These sub-matrices, it depends of the division of our grid. So let's go back to our grid, and we will find we divided 3 vertical lines at the center and 4 horizontal lines horizontally. So therefore we will choose the division vertically, as we said. Therefore we will make a matrix number 1 for the vertical line number 1, and another matrix number 2 for which passes through the second line number 2, and a third matrix number 3 for line number 3. Each matrix is considered as a 1-dimensional steady state, and matrix number 1 will have the variables T1, T2, and T3 and T4 with the neighbors. At the west side it is a boundary condition, and this flux, and at the east side there is the temperature T5, T6, and 7 and 8, which is also unknown. And the variable for matrix number 2, it is 5 and 6 and 7 and 8, and the variable for matrix number 3, it is T9, T10, T12, T11, and T12. So therefore, as we said, we have to divide the big matrix into 3 sub-matrices according to line number 1 and line number 2 and line number 3. So matrix number 1 will take the variables T1 up to T4. Therefore we will cut this big matrix. This is the first edge, and we will name this matrix number 1, and other 2 independent or unknown variable T5, 6, 7, 8. This is the second, and we will cut this big matrix from the other edge here. This is matrix number 2, and this is matrix number 3. So in order to solve this 3 sub-matrices simultaneously, we will have to solve each one by one. And since this is a not rectangular or square shaped matrix, we have to change it into a square shaped matrix. Therefore, since we will keep these 4 variables for matrix number 1, which is T1, T2, T3, T4, we will have to keep the first 4 figures here, and also the other figures, and therefore we will keep all the first 4 element here. Let's start by doing this line will multiply by this line, vertical line, and the rest number these will be multiplied by the other temperature, and will be transferred to the here to be written here in the source term. Therefore we see here all of the numbers are 0 except this one. It will be, since it is the fifth element, it will be multiplied by T5, and it will be here minus T5, and it will be transferred to the right side, and it will be plus T5, and we will give a star symbol at the top of it, and this star symbol will be explained in a few minutes later. Then let's do the same thing for the second row. Since as we said that these 4 elements will stay as it is, which is multiplied by this vector, and the rest of these number will be transferred with its temperature on the right side. Since the only number we have here minus T1, since it is the sixth element in the second row, it will be multiplied by T6, and it will be minus T6, and when we transfer it to the right side, it will be plus T6 or also star. And the same goes for the second and fourth and the third and fourth row. And we see here this is the same as we did in the last slide. This is vertical line 1 as shown in figure 2.14. Let's do the same thing for the other submatrices, which is matrix number 2 and 3. And here, since we have T5, T6, T7, T8, we have to keep these second 4 element. This one we will keep, and the other numbers we will transfer it to the left hand side, which takes each one takes is print for the temperature variable. Now let's do the first row of the submatrix, and we will see that we will keep these 4 numbers, and the only thing left here is this number and this number. So minus T, it will be multiplied by T1, it's minus T1, and when we transfer to the right, it will be plus T1 star. And this one will be multiplied by the 9th element. It will be multiplied by T9, and it will be here written as plus T9 star. And as we see here, T1 plus T9 star, T1 star plus T1, T9 star. And when we do the second row, we keep this numbers and multiply by T5, T6, T7, T8, and the only thing left here is this number will be multiplied by T2, and this number will be multiplied by T10. Therefore, we will write here minus T2 star minus 1 multiplied by T10 plus minus T10. That means here plus T10 star. And when we check it, we see that it is the correct answer, T2 star plus T10 star. So the same goes for the third submatrix, and we can leave it as homework for you. Now we complete the writing of these 3 submatrices, and it shows that each matrix have a square matrix on the left and a matrix or a vector on the right, which holds the source term values. If we focus for these 3 submatrices, we would find that for matrix number 1, for vertical line number 1, we find here T5, T6 star, T7 star, and T8 star. If we go back to the grid, we will find that the source term has the values of T5 star, T6 star, T7 star, and T8 star. That means the unknown variable, which is T1, T2, T3, T4, have a neighboring point that will be act as a source term for this submatrix system. The same goes for submatrix 2, and these neighboring point will take the star symbol as it is shown in this figure. For line number 2, this unknown variables t5, 6, 7 and 8 will have 4 neighboring points at the west side, which is t1 star, t2 star, t3 star, t4 star, and at the east side it will have 4 variables with the symbol star, which is t9 star, t10 star, t11 star, t12 star. These neighboring points also will act as a source term to this submatrix, and also goes for the third matrix for line number 3. Now let's discuss what the meaning of this star symbol. As we said that in order to solve, say, submatrix number 1, the left square matrix on the left side is it must hold numbers. Also the same thing goes for the right source vector, which have to be numbers instead of these t5 star, these symbol t7 star and t8 star. So these symbols have to be changed to numbers. The same goes for the other submatrices, which is finally we have to change these symbols on the right, on the source term, on the source vector on the right, we have to change it into numbers. So therefore these stars mean that first solution, when we start the solution, or it's called the iterative solution, we have to start with assuming a given number of temperature for all the domain. So therefore we will assume a specific number of temperature for each node. Either it is all constant with the same number or it is variable. So we will choose the constant assumption. That means all the domain at iteration equal to 0. Say this the starting point iteration, which is the solution at the base of iteration 0. All the domain have a temperature equal to 100 centigrade or 200 or 0 or minus 14, whatever it is. The thing is, what's the value of temperature we choose to be the first iteration value of all the domain? It has to be equals to some value that is given in the boundary condition of our question. So let's go back to our model, and we will find that the only temperature is given here is 100 centigrade. Therefore we will choose by assuming all the domain have a 100 centigrade, and it will not affect if we choose another number, maybe minus 13 or plus 260, whatever the number is, but this will make the solution will be delayed for a while, and it will eventually give you after a few iterations the specific solution. So all the stars have 100 here, 100, all we substitute with the number 100. Therefore we can solve all the three matrices together, and it will give us the solution for matrix number 1. It will be iteration equal 1. This will be solved, and also here iteration equal 1, it will be also solved, and iteration equal 1, it will be also solved. Let's focus for the first submatrix. Suppose we have the temperature distribution will be for T1, and this is for T2, and this is for T3, and this is for T4. This one it may be 110, and this one 20, and this one 40, and this one 80. So we will check the difference between each node. That means for T1, this iteration it have a value of 110 degrees centigrade, and we subtract this from the previous iteration, and the delta T will be here 10. And for the second node, it will be delta T 20. The third, it will be this is 160, it will be 60, and the last delta T, it will be delta T will be 80. This delta T is the difference between the result of iteration number 1 and the same and the result for the iteration 0. This delta T, we call it residual. So which is the maximum value of residual between these 4 points? Of course, definitely it is 80. So 80 is the difference between the value of the first iteration result and the base iteration, which is the starting point. This 80 degree, we found it very big, and it is not enough to be satisfied to assume that iteration number 1 it is our solution. Therefore, this 80 is considered to be an amount that higher than a specific value that we choose in our solution. Therefore, we will tell the program to add another iteration. It will make it iteration number 2, and we will give the numbers, the results here, which is 110 and 120 and 160 and 180, a star value for to be substituted in the same matrix, and this will be star values, and we will resolve the same matrix here, and it will give us a result for iteration number 2, and the same goes here and here for the submatrix number 2 and submatrix number 3. So therefore, we will check again which is the maximum residual for iteration number 1. Residual here, maximum, maybe it is for node number 3. Maybe there is another residual here for submatrix number 4. It is the biggest one between all the nodal points. Therefore, we will check here, we will find it here, maybe delta T or the residual for the second iteration, it is 800. Therefore, we find this 800 is much larger than a specific point that we chose at the beginning, and therefore we will tell the program to add another iteration 3 for all the submatrices, and the same goes on and on until we reach a maximum residual value of a specific iteration, that is, its value is low or less than the specific value we choose at the beginning. Now the question is, how much value you consider as a specific value you will be satisfied when the residual is within its limits? Of course, it will be very small, and this small value, it depends on the specific nature of the problem. If you are studying temperature distribution, you will choose the residual value between the temperatures in each iteration to be not more than 1 in 100. That means maybe you will assume it 0.01 degrees centigrade, or 1 E minus 3, or 1 E minus 4. Okay, so the smaller this value will be, the higher number of the iteration you will reach this solution. Therefore, when you be cruel and you will assume a lower limit for the accuracy, you will expect that it will take much longer time and much higher iteration number to be reached. If you take 0.1 degree centigrade, if we take this residual maximum value of residual 0.1 centigrade, maybe you will reach 13 iteration, it equals 13, or if you choose another number, 0.01 degree centigrade, maybe you will end with a 200 iteration number. So it depends. When this number goes smaller, the iteration number will go bigger, and this will cost you more time. And if you are studying another field like chemical concentration or something else, this residual value, you will maybe, if you take 0.1, it will be bigger for this field of study. Maybe you take 1e to minus 6. It depends on the nature of your problem. So therefore, as we see here, all these three submatrices are a tridiagonal matrix. So therefore, we can solve it by computer and using the TDMA method. And it may be 3 submatrices or 15 submatrices. It depends on the cut of your grid, how many lines, vertical lines, or maybe you follow the horizontal lines. So therefore, you will use TDMA method in order to each iteration you compute the residual for each nodal point, which is I, and then you will calculate this value by taking the absolute value of the difference between the same temperature value with this new iteration and with the old one, and will you be end with a value that will not have to reach our residual maximum value, which is assumed at the beginning of the program, which is 0.01 degree centigrade. So in our case, it will ended with iteration number 80 iteration. It will cost us to reach the final solution, which is its accuracy is 0.01 degree centigrade. And unfortunately, as we said, this method requires us more execution time to be to reach the convergence of this correct solution. If we compare this with the direct method, that is solved directly using the calculator by using the Gauss elimination or Jacobi or whatever the method is. And especially when the case is through 3D, it will be a huge matrix, and you have to deal with such submatrices method. Therefore, all the computer programs is designed to subdivide your domain, because they deal with a huge array of grid points, and therefore it will take time to converge to your accurate value of results. All of these programs like ANSYS Fluent or CFLux or others, it will take the same procedure and will give you the iteration which the solution converged to your result. So in this way we end with the Cartesian coordinate system, and we change to the polar coordinates, as we see here for the steady state diffusion problem. For the polar coordinates, we have figure 2.15. As it is shown, there is a hollow pipe, which flows inside it a hot or cold fluid, and there is a circular fin which is attached to this pipe in order to dissipate the heat of this fluid to be a coolant. This fin have a rectangular shape, and it have a base temperature T base, the same as the surface of the pipe, and it is assumed to be insulated at the edge of this tip of the fin. And this fin has inside radius RB and outside tip radius RA, and also it have a thickness of delta. The base temperature is T0, as we said, and the edge is perfectly insulated, and it is exposed to an environment temperature, say air or water, whatever it may be, with a temperature of T infinity if the thermal conductivity of the fin material is K, and it is the convection heat transfer coefficient is H between the environment and the fin material. It is required to find the temperature distribution along this fin using the finite volume method. Knowing that the one-dimensional steady-state energy equation of this problem is given in equation 261. As we see here, 61, it have differential equation 261 have the coordinates of radial coordinates 1 over r d by dr r dt by dr minus m square t minus t infinity. This minus sign will tell us that the source term, since this shape is a regular shape of the term, it is a source term, and since it is negative, it will be a heat sink. Heat sinks mean that if this is a fin, in the heat sink, the temperature of the domain will be decreased with the increase of x, and it will take the minus sign. If the temperature will increase, it will be a source term, because this temperature will increase in the direction of increase of x, and therefore this will take the positive sign of the source term. Therefore, we have to distinguish directly by looking on the general differential equation, and we see the sign of the source term. If it is negative, it is a sink term, and if it is a positive, then it is a source term. The m square is given by this value, and to start our solution, we will continue with the same procedure by integrating this differential equation once from west to east and multiplied by the volume of the element, which is this slice of elemental area with a thickness of dr. So therefore dv will be equal to 2 pi r, which is the length of the arc, multiplied by the thickness of it, which is delta. Then we substitute the limit of integration, and it will reach, and we also substitute or use the central difference, most accurate method, second order accuracy, and we will end with this equation, which is algebraic, equation 262. Now we will start with the internal nodes. So we rearrange equation 262 and put all the parameters, that is multiplied by the figure t point on the left side and the rest at the east side, and we will find a strange parameter here, which will go to be, which will be SU, and this figure, it will be SP, and this parameter, which is multiplied by t west, it looked like this one, therefore it will be A west, and this parameter, it looked like the same as this second figure, and it will be A east. Therefore all of this will be A west plus A east minus this SP. So therefore we will have the assembly table for the internal node as shown in this table. Again, we do the same thing for the control volume number 1, which is at the base of the fin, which have a boundary condition T naught instead of T west, which is at the interface. This is a small w, sorry, and R small west small w equals R base, which is given at the boundary condition. So again, equation 263 for the control volume for node number 1 can be written as the form here, equation 265. And since it is at the west side, there is no A west, it is 0, and this will be both together will represent SU, and also this will represent SP, and this one A0 for A west, and this one will be A east. So we rewrite again this for node number 5, which is at the tip of the fin, and since it is insulated, perfectly insulated, so therefore the gradient at the east interface it is 0. Therefore equation 267 will be written and rearranged as shown in equation 268, and gathering all the parameters of T point on the left side and the other on the right side, and therefore there is no A east value, it is 0, and this parameter on the right, far right, it will be SU, and this goes for SP, and 0 for A east, and this one for A west. So since we have 3 tables for each node zone, therefore we assemble them to have this assembly table which have 3 zones, and again we substitute the given number in this homework example, and predict the 5, if you choose 5 control volume, 5 algebraic equation with 5 unknowns, and we rewrite the matrix system with 5 unknown variable and solve it by using MATLAB or your scientific calculator to reach your what is required in this question. The last thing we study in this chapter is the spherical coordinate system for the one-dimensional steady-state diffusion problem. Here we have a hollow sphere with an inside diameter of big R1 and outside with an inside radius of big R1 and outside radius of big R2, and with a boundary condition the inner surface constant temperature T1 and outer surface with a constant temperature T2. The thermal conductivity of the sphere material is constant K, and it is required to find the temperature distribution along the thickness of this sphere material. And knowing that the one-dimensional energy equation for this problem is given in differential equation number 270. As we see here, we use the Legendre equation for describing the temperature differential equation for this problem, which is y over r square multiplied by d by dr r square k dt by dr equal to 0. So we start our solution by integrating this differential equation from west to east and multiply it by dv, and dv for this elemental area, it will be the surface of area of any slice which is covering this sphere with a distance small r and with a thickness of dr. Therefore it will take the volume of this spherical shape cover. It will be the surface of a small sphere, the surface of this sphere with a radius small r multiplied by the thickness of this sphere dr. So the surface of any spherical shape, it is the derivative of the sphere volume. Therefore, this dV will be equal to 4 pi r square dr. So we substitute this dV into this term and opening this differential equation with substituting the limit of integration, and we will end with algebraic equation 271. So when we start our solution for the internal node, we will collect the parameter which is multiplied by t point and put it on the left, and the other parameter on the right, and we will write it at the general discretization form, which is shown in equation 273, and we will add a zero value for this equation. It will be plus SU term for the sake of programming. Here SU equal to 0, and there is no SP here, it will also equal to 0, and this one the same as this one, it will be I west, and this one is the same as this one, it will be A east. So therefore A point will be A west plus A east minus SP, which is 0. So this is the table parameter that shows the parameter for the internal node. So we again make the table for control volume number 1, which is at the inner surface of the sphere. So therefore the temperature is at the interface is T1, big T1, and R west is equal big R1. So we substitute this in equation 271, and we will have equation 274 with this strange value. It will be as SU, which hold the value of the boundary condition T1, and there is no A west, it is 0, and this parameter, the last parameter before TP, it goes for SP. No A west 0, and this is A east, it will be here. So equation 275 represent the general discretization form for control volume number 1, and all the parameters it is given in this table. So again we rewrite the discretization equation for control volume number n, which is at the outer surface of the sphere, which hold a boundary condition T2 at the east side, and R east will be equal big R2 as given in the boundary condition. So substitute these into equation 271, we will have equation 276, and the last term will represent the SU term with the boundary condition multiplied T2, and there is no T east, A east 0, and this last figure before the T point it will be minus SP and this will be A west. Therefore the general discretization form of the control volume number 5 will be written as shown in equation 277, and the parameter is shown in this table. Therefore we will have 3 tables, and when we assemble them we have the general assembly table for this problem. And for any question which have the case study of 3-dimensional diffusion problem with the spherical coordinate with the same boundary condition T1, or temperature at the inner face known and temperature at the outer face it is known, therefore we can use this general assembly table to make a number of algebraic equation and rewriting the matrix equation. Then we will solve it using MATLAB or our scientific calculator. So therefore we will end this chapter with a number of unsolved projects as a homework. All of these the majority of these problems have a regular shape fin, which is a one-dimensional, and we see here problem number 1. The shape is a conical spine fin of given length and radius, and the T-base temperature, it is T0 given 100 centigrade, and the tip is perfectly insulated. That means no heat flux at the edge. This fin is exposed to T infinity, which equals to 25 degrees centigrade of the environment. If the thermal conductivity of this fin is constant and the convection heat transfer between the environment and the film material is also constant, it is required to find the temperature distribution of this shape using the finite volume method, knowing that the governing differential equation is given here with a value of m squared, which equals the parameter that is shown, the equation that is shown here. When we start the solution, we have to take into account the change of area along the x direction. Again, we will say that numbering the control volumes, it doesn't matter if you take the direction from left to right, or you take the reverse direction from left to right. It is the same thing, but the thing is you have to put each temperature with with the corresponding position of it. Problem number 2, another shape will be studied, which is a concave parabolic spine fin, which have the same data given in problem number 1, but with a different shape of differential equation and with the same value of m squared. Also, it is required to find the same temperature distribution when the fin shape is changed, and this calls for the third shape, which is convex parabolic spine fin, and with a different shape of differential equation and the same m squared value. And we can solve the three problems together, and we can compare which fin is the best performance of each shape it is. So P number 4, it is another shape of fin. It is a longitudinal fin of triangular shape with the same data. The base is 10 centimeter with the specific length 1 meter, with the same K and H values, and its shape of the differential equation is different from the others, and the same thing is required. So in problem number 5, we have a longitudinal fin of a concave shape, concave parabolic profile with this given differential equation, and P6 with a convex longitudinal fin with a convex parabolic profile and with this shape of differential equation. So you can also compare the problems 4 and 5 and 6 and find which is the optimum performance, which shape have the optimum performance of a fin. And the last two problems, it is a two-dimensional case study. Problem number 7, it is a two-dimensional rectangular plate with a length of 1 meter and thickness 1 centimeter, as shown in figure 7. The thermal conductivity of the plate is constant, and it is given here, and it is required to calculate the temperature distribution along this plate using the finite volume method. With assuming a uniform grid, forcing us to take delta x and delta y equals 20 centimeter. That means if we have 1 meter and divided by 20 centimeter, that will mean it will be 5 control volumes in the x direction, and x equal 5, and 1 meter length height of the y direction divided by 20 centimeter, so ny will be also 5. So the general number, all number of control volume will be 25. That means we will end with a general matrix system equation which have a 25 algebraic equation with 25 unknowns, and this differential equation is given and we have to solve it and find the 25 variables of this plate. Again, the same this boundary condition, all the edges have a 0 value temperature except the north face have a 500 degree centigrade. So problem number 8, the same plate with a different boundary condition, both the north side and the east side have a 0 temperature, and the east and the west side and the south side have a perfect insulation with a 0 flux value. The governing differential equation is given as here, and we see the source term. That means there is a heat. Since it is positive, there is a heat source here, and it will increase definitely the temperature. So this value of source, heat generation source per unit volume is given here, and the same delta x equal delta y equals 20 centimeters, and the same dimension 1 meter by 1 meter. That means we will reach for the solution of 25 variables, t1 up to t25, and the boundary condition is this as I described earlier, and the general differential equation is given here. So we reach the end of this lecture. Thank you.